So far we've talked about the definition of entropy now from a microscopic standpoint. Kb natural log of omega, where omega is the multiplicity or the number of microstates. Let's say number of microstates. Or you might call it the multiplicity. And so the statement that a system has entropy increasing just means that it's moving to states with higher and higher multiplicity, which is another way of saying that it's ending up in the most likely state. So systems which are isolated, S will increase over time until equilibrium, which is another way of saying that they move towards macrostates with higher multiplicity, which means that they're just moving into more likely, or states which are more likely to occur. So that's the kind of essence of the second law from a microscopic standpoint. Okay, let's do an example. Just an example of how to use this in a problem. So let's say you've got 1 gram of ice here. So it's ice, and it's in contact with some kind of reservoir, which is adding heat to the ice, and then the ice is going to end up melting into a puddle of water. So it melts into water. And the claim is that the ice here has some omega initial, some multiplicity. The macrostate is the block of ice, and then there's a certain number of ways to arrange the atoms so that the total appearance of the ice is unchanged. And then the same thing for the water. The water is a macrostate, but it has some certain number of ways to arrange all the atoms to leave the macrostate unchanged. So it has a certain number of microstates, omega f, and we want to know how much did that, by what factor is omega f bigger than omega I. Okay, so before I do it, let's do a little bit of a review. So just a little bit of review. I want to calculate the entropy change of the ice when it melted like this. And which of these formulas would I use? So got 4 options. Q over T ice, Q over T res, so that's the temperature of the reservoir. This one, which has the natural log of the T res over the T ice, and then this one, which has some temperature Tf over Ti plus R natural log Vf over Vi. So a lot of times students have difficulty deciding which formula to use when they're calculating entropy change. So see if you can remind yourself or practice thinking about which one of these you would use. Go ahead and pause the video and then see if you can determine the answer. Okay, did you select your answer? All right, so remember that the best way to do it is to start, you can always start with something like this. ds for the ice is the heat added to the ice divided by the temperature of the ice. And then delta S is the integral of ds, right? So it's integral dq, heat added to the ice, divided by the temperature of the ice. But because the melting takes place at constant temperature, I can pull this outside. And so I have 1 over T ice, integral dq, which is just q. So this is the heat added to the ice over the temperature of the ice. So if you chose answer A, that's the correct one. Okay. It can't be B because the temperature of the reservoir shows up here, and delta S, this would be okay if you were calculating the entropy change of the reservoir, but the temperature there is the temperature of the object which heat is being added to, right? So if I want the entropy change of the ice, I can't use B. This one is good for if the temperature is changing. So in some cases, like if the ice is heating up, I can't pull the T ice outside of the integral, and then I end up with dt over t, and I end up with that natural log. So this third one, choice C, is if there's a heating going on, but there's no heating here, it's just melting. The last one you can't use because it's for an ideal gas. And the dead giveaway that it's for an ideal gas is the presence of R, which is the ideal gas constant. So any formula that has R in it can only be used for a gas, not for a liquid or a solid. All right, so A is the right answer here. So let's proceed with the problem then. All right, so delta S for the ice is the heat added to the ice divided by the temperature of the ice. Because the temperature is constant, so it's melting, I don't need to do any integral here. And the heat added is going to be, of course, the mass of the ice times the latent heat of fusion, since I'm melting it, divided by the temperature of the ice. So that's the way I would calculate the entropy. Now, I want to know by what factor did the multiplicity change. So now here is where I'm going to use the new ingredient, which is delta S for the ice, is Kb natural log omega final over omega initial. So I'm making the connection between entropy and multiplicity, or number of microstates. So we can substitute those in. We get natural log omega F over omega I is equal to m, mass of the ice, latent heat of fusion, Kb, temperature of the ice. And so omega F is equal to omega I times E to this number, m ice, LF, Kb, T ice. And let's plug in the numbers. There we go. Now you can tell this is going to be a ridiculously large number because it has Kb in the denominator. Kb is really, really small, Boltzmann's constant. And then it's in the denominator, so I'm going to end up with a really, really huge exponent. So these kinds of numbers are mind-boggling. They're the kind of numbers that you never get anywhere except in statistical mechanics. So plug in the numbers. It's e to the 8.8 times 10 to the 22. Okay, that's a ridiculously large number. You've probably never thought of a number this big before in your life. It's not really something that humans can think about. It's not 8.8 times 10 to the 22. That's already a ridiculously large number. It's e to that power. So it's really, really, it's like your calculator won't even give you any number if you plug this in. Sometimes people like to express this as a power of 10. You can just convert it from log base e to log base 10 as follows. I can use e is equal to 10 log base 10 of e, like this. So then I would get something like this. So just converting the e into a power of 10. And this exponent, I'm out of space here, but let me write it somewhere else. So let me write it up here. Omega F over omega I is equal to 10 to the power 3.8 times 10 to the 22. So ridiculously large. What does it mean? It just means that there is way more ways of arranging atoms to leave the overall macrostate unchanged. So way more microstates in a liquid than in a solid. And that makes sense because a solid is an ordered crystal. I can move the atoms around, but they can only be in certain places in the crystal, whereas the liquid, they can be kind of pretty much anywhere. So I have a huge increase in the multiplicity when I melt the ice to water.